Walk onto the floor of any modern factory or power plant, and the environment looks calm and routine. Visually, everything appears to be running perfectly, but shifting our perspective to look at the acoustic data reveals a completely different reality. Mechanical equipment and high-voltage systems rarely break down without warning. Long before a valve bursts or a cable snaps, failing components begin to leak high-pitched acoustic energy. Inspections that rely solely on human sight remain blind to the earliest, most preventable stages of catastrophic equipment failure. Frequency spectrum chart illustrates our biological limits. The specific warning sounds of pressurized gas leaks and electrical faults exist well above the 20 kHz threshold of human hearing, way out in the ultrasonic range. Standard single microphones are useless here because they record a flattened, omnidirectional wall of noise. They register the chaos, but have no physical way to isolate or locate the source of an ultrasonic warning sign. Since our ears cannot filter the noise and our eyes cannot see the frequencies, the only way to detect these threats is to build a technology that translates inaudible sound into visual data. To prevent loud factory noise from ruining the math, the software filters out low-end rumbles, isolating a high-frequency bandwidth between 2 and 96 kHz. This process translates physical acoustic pressure directly into an electrical signal, with a much higher signal-to-noise ratio than traditional microphones. Shrinking this mechanical process to a monolithic microscopic scale eliminates ambient vibration, allowing for the capture of ultra-pure, high-frequency data. The true power of the technology comes from packing massive geometric arrays, up to 136 individual microphones, onto the face of a single device. An incoming sound strikes the microphones asynchronously, hitting different nodes at slightly different microsecond intervals. The software utilizes time difference of arrival to measure those delays and calculate intersecting lines, tracing the wave back to its exact three-dimensional point of origin. Analyzer software then filters out background noise, turns that location into a color-coded heat map, and projects it directly onto a live optical image in real time. The camera applies spatial geometry to force invisible sound waves to reveal their exact physical coordinates on a screen. Out on the power grid, partial discharge is a silent threat that degrades equipment in plain daylight while emitting only ultrasonic noise. An acoustic camera reveals localized, violent ionization of the air around the insulators, a severe failure point that is completely invisible to the naked eye. The system identifies a high corona discharge, a partial electrical leak that precedes catastrophic equipment failure. Notice how the sound anomaly floats against the blue sky. Without this acoustic map, there is zero visual evidence that electricity is bleeding off the insulator. Analyzing the unique acoustic fingerprint of the noise allows the software to categorize the exact type of failure in real time, pinpointing corona, floating, or surface discharges. Identifying these localized ionizations early prevents them from escalating into massive, cascading electrical grid blackouts. Engineers can now diagnose catastrophic electrical threats instantly from a safe distance, without ever shutting down the power system. In large industrial complexes, pressurized gas and air leaks are a constant financial drain, venting resources and money into the atmosphere. The old method of manually inspecting miles of pipes with soapy water has been replaced by a single operator sweeping a facility with a handheld acoustic screen. The device calculates the estimated volume of a leak and instantly displays the financial cost directly on the touchscreen. We have engineered a way to tame a chaotic ocean of acoustic data into immediate, actionable visual intelligence. These sensory bridges translate high-stakes industrial data into a visual language, revealing the invisible forces that dictate the reliability of our critical infrastructure.
We are FMG Tech. Contact us for more information. Visit fmg-tech.ir.